start again. So next speaker of this morning session is Emilio Corso from ETH Zurich. He will speak about folding dilating shapes, a journey from Euclidean to hyperbolic geometry.
Thanks a lot, Alfonso, for the introduction, and I'm deeply grateful to the organizers for giving me this first chance to take part in a DinAmicI seminar meeting. Let me start off right away with the opening question with which I phrased in the abstract, namely, what happens to a progressively dilating body when you fold the ambient space in which it lives according to some prescribed procedure. And as an example, you are invited to bear in mind throughout the talk, not least because it was already mentioned by Mark in the previous lecture, consider expanding circles in the Euclidean plane and then fold the space along the integer lattice so that it becomes a torus. And I tried to draw something here. So you see progressively dilating circles, and what the result is on the torus. So you start with the first smaller circle, which is in red. You see that the orbit goes along some path. Then as you expand the circle, you have the green one. It travels along some other path. Then you have the blue one. You can sort of see that it fills in the space ever more as the radius goes to infinity. So the question is, what happens, what are the ergodic properties of these expanding circles as the radius goes to infinity? Not only, of course, in this setting, but in a general setting. And to the best of my knowledge, this question was first formulated in full generality in the 80s, at the beginning of the 80s, by Dennis Sullivan. So if anything, this talk serves the purpose of paying tribute to this year's Hubble Prize. But of course, I'm trying also to give at least partial answers to this problem. So let me start with the general formulation, which is consider N to be a compact connected Riemannian manifold, and let N tilde denote a Riemannian universal cover. With covering projection, say, denoted by pi, from N tilde to N. So you can imagine as that N tilde is the initial ambient space, and N is what results after some folding, according to some projection, according to some procedure. And then consider some family of homostheties in N tilde, which describe the dilation. So this is a collection of homostheties, Riemannian homostheties. So there is a rescaling of the metric by a certain ratio. Homostheties with a ratio tending to infinity as t goes to infinity. And your initial shape, your initial body, can be described in terms of a mass distribution. So you consider an initial distribution mu, a Borel probability measure on N tilde. So of course, in terms of distribution properties, this measure theoretic point of view is pretty convenient, and denote by NT the push forward of mu under HT. So it's a dilated time t of this measure, and then you project it to the space N, to the folded space N. So let me call this MT. It's the projection of the mu t. And the question, as I already formulated vaguely, is examine, so this is due, as I said, to Dennis Sullivan in this generality. Describe the set of weak star limits of the MT as t goes to infinity. So of course non-empty because I'm assuming I'm starting with a compact manifold. What is this set? Or somewhat less pretentiously, you might want to ask, determine sufficient conditions under which you have equidistribution, meaning the unique weak star limit of the MT as the measure goes to infinity is the renormalized volume measure on n. So determine sufficient conditions for equidistribution. i.e. MT converges to, say, the volume measure on n renormalized by the total mass. Now, this question, as already mentioned by Mark, was first addressed by Bertrand Randall. So first addressed by Bertrand Randall in 1984 in the setup of constant curvature. So both in the Euclidean and in the hyperbolic setup. Hyperbolic case. And let me start this journey by the Euclidean case. What happens when we are in flat geometry? So in this case, we have that, well, we can take n tilde to be Rd, universal cover. And for simplicity, let me take the standard integral torus. N is d-dimensional torus Rd mod Zd. Of course, pi is the projection that sends each point x to its equivalence class mod Zd. And let me consider the family of standard homotheties, linear homotheties. So let me define HTX to be simply multiplication by x. So the standard linear homothetity on Rd. Now, in order to examine the ergodic properties, the distribution properties of this of my measures MT, I need to integrate, of course, against continuous functions. So let me fix a continuous function on the torus, and for the purposes of what comes next, let me assume, it's convenient to assume that its Fourier transform is in little L1 of Zd, where, let me recall just also to fix notation that the Fourier transform of a function on the torus is simply the integral of the torus of, of f of y e to the 2 minus 2 pi I and scalar product with y with respect to this is my notation for the normalized Haar measure, the probability Haar measure on the torus, the standard Lebesgue measure, which gives to the torus mass 1. So assume that the Fourier transform is integrable. This certainly happens once you assume that f is a sufficiently high regularity class. Those type of functions, for instance, already see infinity functions are dense in the space of continuous functions, so there is no loss of generality in assuming this, I mean, for the purposes of my problem. So it becomes at this point a rather elementary exercise to compute what is the integral of f with respect to mt, the measure mt, in terms of my starting measure mu. Because this, well, of course, this condition, this integrability condition for the Fourier transform allows me to exchange integral and sums. By dominated convergence, I can decompose the function in terms of characters. So this becomes a sum over all n in Zd of my Fourier coefficient. And then I have the integral over Td over the torus of my character e to the minus 2 pi, e to the 2 pi I, and say x plus Zd in DMT x plus Zd. But now I unravel the definition of my measure mt, and so this integral becomes the integral over Td of e to the 2 pi I n dot x d mu t. Remember that, sorry, this is now over Rd. Remember that I defined the mt as the projection of mu t on the torus. But here I can write again, mu t is the push forward under my dilation ht. So this I can write as the integral over Rd of E, and now let me write it in this way, e to the minus 2 pi I minus Tn dot x in d mu. Why sorry, what did I? Now, why have I written this in this way? Because now this becomes the Fourier transform of the measure mu at the point minus Tn, where, of course, the Fourier transform of a measure is defined by integration against characters. It's the right generalization of the Fourier transform of a standard L1 function, e to the minus 2 pi x c y in dy. In d mu x. Sorry, d mu y. So you see that now we can write the difference between the integral of f with respect to mt and the integral of f with respect to the standard Lebesgue measure. Well, here I have this sum, but at 0, the Fourier coefficient, I have 1 as the term corresponding to the Fourier transform. The Fourier coefficient is simply the integral, so I'm left, the integral with respect to the Haar measure, so I'm left with the sum over all n, over all integer vectors, non-zero integer vectors, of f hat n mu hat minus Tn. And so I've reduced my geometric problem, distribution problem, to a Fourier analytic problem of examining the behavior of the Fourier transform of the measure mu at infinity. And this leads me directly to a theorem which was proven by Strichertz in 1989. So if the Fourier transform decays along integral rays, so if mu hat of Tn goes to 0, for any, as t goes to infinity, for any n, of course, non-zero, then I have that mt of f converges, so this is notation, shorthand for the integral of f with respect to mt, converges to mtd of f for any f as above, and hence equidistribution holds for the mt. Let me just say in words that this condition is clearly also necessary, because as soon as you have one non-zero integer vector for which this condition is not verified, then take the corresponding character, it will have Fourier transform on the torus, it will have Fourier transform which is equal to 1 at that integer vector and 0 elsewhere. So if you don't have convergence to 0, then the integral for that character will not be infinitesimal when integrated against mt and the difference with the integral with respect to the Haar measure. So this is a complete Fourier analytic characterization in terms of the measure mu of equidistribution. So what remains to do is to verify this Fourier analytic condition in concrete instances. And so let me list a few examples of measures verifying this condition. And let me give, in order to, let's say, encapsulate all the examples that I have in mind, let me say that a measure mu is called, this is a traditional terminology in harmonic analysis, is a Riemann measure. If I assume something a little stronger, if the Fourier transform decays to 0, not just along rays, but uniformly on over rays. So if mu psi tends to 0 as psi tends to infinity. Now this its relevance already from the Riemann-Lebesgue lemma, the classical Riemann-Lebesgue lemma, on Fourier decay of integrable functions. There has been a lot of research in harmonic analysis revolving around this class of measures. Here, for the purposes of this talk, I'm just interested in some examples of geometric interest. So let me also, before I list some 2 or 3 examples of this classes of examples of Rashomon measures, let me also point out at this point that if you are Rashomon, or more generally, if your Fourier transform decays along all rays, then the projections of the mu t, not only on the integral torus, of course, but on any torus, so, or any quotient of Rd modular lattice, will equidistribute. And here's again a complete characterization. So examples, well, of course, by the classical Riemann-Lebesgue lemma, if mu is absolutely continuous with respect to Lebesgue on Rd, well, then it is surely Rashomon. It's because its Fourier transform will coincide with the standard Fourier transform of its Radon-Nikodym derivative, and it tends to 0, as we all know. So this implies mu Rashomon. This is a rather elementary example. So you might phrase this by saying that sets of positive, if you consider a set of positive finite Lebesgue measure, and you take the uniform measure, renormalized uniform measure on it, well, then it equidistributes in the torus under dilation. Well, depending on your geometric intuition, this might seem more or less obvious, but certainly what is not clear a priori is the behavior of more singular measures. For instance, the volume measure associated to supported on a Riemannian submanifold. That's far less clear. And so what happens if mu is a volume measure, renormalized, so mu, renormalized volume measure on some C in Rd, which is a compact Riemannian submanifold. For instance, a sphere. Just consider the case of a sphere. Riemannian submanifold. So well, in general, of course, you cannot expect equidistribution. There are some obstacles. For instance, no equidistribution in general. Well, for instance, take C to be the open unit segment in a direction V, where V is a vector V1 up to Vd in Rd, where the VIs are rationally dependent, so are dependent over Q. Then the problem of equidistribution of dilating, of the distribution of asymptotic distribution properties of dilating sets in this case it amounts simply to analyzing the orbit of the origin under the translation flow on the torus in the direction of V. As we all know, when the coordinates are rationally dependent, there's no equidistribution. The trajectory of the translation flow stays confined to a proper subtorus. And so it doesn't equidistribute under dilation. More generally, if you take higher dimensional examples, if C is confined to lie on some rational proper affine hyperplane in Rd, then again, for essentially the same reason, equidistribution cannot hold. And even more generally, it turns out that curvature poses some obstruction to equidistribution. But on the positive side, there is a result in harmonic analysis, say in the theory of oscillatory integrals, that says that if C is compact, is a compact hypersurface with nowhere vanishing Gaussian curvature, then then the Fourier transform, then the measure, the volume measure supported on it is Rashomon. Curvature, then mu is Rashomon. And so, for instance, as a very elementary example of this, spheres equidistribute when dilated and projected to the torus. Or not only in spheres, it suffices to have nowhere vanishing Gaussian curvature. Or more generally, even, it suffices to have at each point at least one of the principal curvatures, which does not vanish, and the same result would hold. These are very highly involved results. I mean, the proof is highly involved in harmonic analysis, but here I'm just interested in listing some examples. If you want to understand what happens for lower dimensional submanifolds, then there are also conditions which can be phrased and which ensure that the measure is Rashomon, so you have equidistribution. For instance, an easy way to formulate this is that if a real analytic manifold does not lie on any affine upper plane, then again you have this Fourier decay. So more generally, well, it's not more general, but for general dimensions, if C of any dimension does not lie, is real analytic, and does not lie on any proper affine hyperplane, on any affine upper plane, then mu is Rashomon again, and you have equidistribution. And the last class of examples I would like to mention are, so these are smooth measures supported on submanifolds. What happens to measures supported on fractal sets, for instance? Now, these have attracted considerable attention in recent decades, especially in connection with the problem of estimating the house of dimension of some classes of fractal sets from below, which is notoriously harder than estimating the house of dimension from the above. But so let me be, in the interest of time, let me be a little vague on this fractal measure and just say that if mu, so say that I fix a family, a finite family, Fj of is a family of affine contractions. So I'm aiming at self-similar measures, self-affine measures. So let me briefly recall the definition. It's a family of affine contractions on Rd. And you give yourself also a probability vector, P, a probability vector. Then these two things uniquely determine what's called the self-affine measure. So there is a unique Borel probability measure which is self-similar with respect to this two data, meaning that mu is the sum, is equal to the sum over j of pj, mu composed with fj minus 1. So there's a unique measure satisfying this condition. And so it's the average, according to the probability vector P, of all its images under this affine contractions Fj. So it's called the self-affine measure. Determined by the Fj and P. Well, there are some algebraic conditions that can be concretely checked and imposed on this on the set of affine contractions, which ensure again that the measure mu has Fourier decay. So there are explicit algebraic conditions that can be imposed. Sorry. That can be imposed on the Fj, ensuring that mu is Rashomon. For instance, just to by way of example, if you take the standard Cantor-Lebesgue measure on the middle lambda Cantor set, say, where lambda is smaller than 1/2, then it holds that you have Fourier decay if and only if this lambda has the property that its reciprocal is not a Piso number, if you know what that means. And the same is true for all Bernoulli convolutions, which is in some sense continuous, can be continuously thought of as continuous extensions of this Cantor-Lebesgue measures. But I don't want to get into any detail, nor I would like to elaborate more on this fractal measures, because it's now time to refine the question of equidistribution that I had at the beginning and ask, well, now I have a qualitative statement. I have this equidistribution. What about an effective version? As you know, as we know in dynamics, we are always interested in establishing effective, especially in homogeneous dynamics, but not only. We are interested in establishing effective versions of qualitative results. So the question now is, what about effective equidistribution? Well, if you go back to the elementary argument that I run at the beginning, well, it is clear that as soon as I have some quantitative information on the decay rate, not just decay rate, but some quantitative information on the decay rate of mu, of the Fourier transform of mu, then I can immediately upgrade the statement to an effective version. And let me phrase this in this way. So if I have a Fourier decay of this type, so if mu hat of psi decays like psi to the minus s halves for some s, the reason why I'm dividing by 2 is well known to all people knowing a bit of fractal geometry, but it will become clear in a moment. For some s, then the corresponding rate transfers to the equidistribution. So I have that the difference between the integral of f with respect to mt and the integral of f with respect to the Haar measure is bounded, some constants depending on mu and s, by the L1 norm of the Fourier transform of L times, well, t to the minus s halves. So I have this rate of equidistribution. And now what's the meaning? What's the geometric meaning of this decay rate minus s halves for, minus s halves for the measure? Well, it implies, it is intimately tied to the fact that its support has house of dimension at least s, or at least.
M is mu, right?
What?
M is mu.
M. Where is M?
Measure in the circle.
MTD. No, that's the Haar measure. I'm estimating the difference between the integral of f with respect to m to mt.
Mu is the measure supported on the.
Nu is the original, my starting measure, which describes somehow the original shape that I want to dilate and then project. Yeah, that's mu is always the original measure. And so this condition, this Fourier decay condition, is connected by some result which is known as Frossmann lemma in fractal geometry, that tells you that if you have such decay, then the support of the measure has house of dimension at least s, or let's say at least the minimum between s and d. D is the ambient dimension. It is not equivalent. The condition is not equivalent, but for the classes of examples I'm considering here, it is actually equivalent. And let me just say that if C is as before, so is a compact hypersurface with nowhere vanishing Gaussian curvature, as before, then a result of Littmann in the 60s says that you have the expected optimal Fourier decay for the measure mu. Mu, again, is the volume measure on C. So this is the rate is minus t minus 1 over halves. So it's precisely the dimension of the hypersurface. And actually, the corresponding equidistribution statement is due to Randall. Was properly phrased by Randall in 1984. Let me now move on to the next part of our journey, which is the hyperbolic case. I have somewhat examined the flat case. Let me consider now the hyperbolic case. What happens in the hyperbolic case? So, which was again considered first by Randall, and I'm not aiming for the utmost generality here, and instead I'm profiting from the fact that Jens has already introduced the upper half plane model of the hyperbolic plane in his talk, and so let me take advantage of that and restrict to the two-dimensional case, which is already quite interesting. So let me now consider that, so now n tilde, my universal cover, is the hyperbolic plane, which I'm considering the upper half plane model. So equipped with the Riemannian metric gxy is dx squared plus dy squared over y squared. And n is now the quotient of h by a co-compact lattice. So it's gamma mod h, where gamma is a discrete subgroup of PSL2R co-compact. So co-compact discrete. I can now consider, for instance, expanding circles, as already mentioned by Mark. So let me define mu t to be this time. So I fix a center of my dilation. So let me fix a point x0 on the universal cover on the hyperbolic plane, and consider mu t to be the hyperbolic length measure, always renormalized to be a probability measure, hyperbolic length measure on the boundary of the ball centered at x0 with radius t. The ball, of course, in the hyperbolic plane. So I'm considering really circles in the expanding circles in the hyperbolic plane, and then projected down to a compact Riemann surface, to a compact hyperbolic surface. What happens? As already mentioned by Mark, again, here, equidistribution holds. So, and this is, again, due to Randall.
Well, I guess that really goes back to Margulis, no?
Yes, and I'm mentioning this too, yeah, in the last, yeah. Margulis says even more as equidistribution in the unitangent bundle. I'm mentioning this in a moment, yeah. So what is due to Randall is the extension to any dimension. With an effect, sorry, I'm missing a word, an effective equidistribution in any dimension. That's what exactly is due to Randall, yeah. Randall. So the mu t equidistribute. But actually, so before giving the precise, a more precise version of this result, let me upgrade the problem, as already suggested by Jens. I'll upgrade slightly the problem, and considering instead of just the circles on the surface, I upgrade the problem to the unitangent bundle. So an upgrade of the problem. So replace H by its unitangent bundle. So the set of all pairs CV where V, the norm of V is 1. Replace gamma mod H by the unitangent bundle of gamma mod H. So now, as this is well known, this is diffeomorphic to PSL2R, and this descends to a diffeomorphism of this unitangent bundle with gamma, the homogeneous space gamma mod PSL2R. And I replace my circles with the set of points in the unit tangent bundle, which are simply the normal, the outward pointing normal vectors to the circle at each point. So I replace the boundary of the ball, x0t, with what I call cx0 of t, which is the set of all pairs z, say nz, where z is in my circle down, down onto the surface, and nz is the outward pointing normal vector to the circle, to the boundary. So I should have a picture here, yes, on the modular surface, what happens. Now, this is not a co-compact quotient, of course, but since it's the example that we all know, just to clarify what happens, here you have expanding circles. In blue, you have the picture in H on the hyperbolic plane, and in yellow, you have what results after identification by the lattice SL2Z, and you see this picture should somehow convince you that as the radius increases, here again, the circle fills up the space ever more uniformly. And here what I'm considering actually now in this upgraded version of the problem is not only this trajectory depicted here, but also you should think of at each point you have the normal vector pointing outwards. Why I'm considering this? Well, this set that I'm considering now, this admits actually a generally dynamical interpretation, because this set x0t is nothing but the image at time t of the geodesic flow, under the geodesic flow, of the unit tangent space at my center point. So this is, so denote by phi t the geodesic flow on the unit tangent bundle of gamma mod h. And then this circle with the collection of outward pointing normal vectors is simply phi t of the unit tangent space at my point gamma x0, say, to the surface. So you start with the point with all possible direction, you follow the geodesics until time t, you get precisely my circle ct with the outward pointing normal vector. And now, as already mentioned, you can examine the behavior of the circles in the unit tangent bundle. What is the distribution of the circles as t goes to infinity? And that's a result that was mentioned by Margulis. It's one of these many contributions of his PhD thesis. But it's a non-effective result. So Margulis, I guess it's 1969 or something. The circles Cx0t equidistribute inside the unit tangent bundle. Now, of course, you might ask, what is the natural uniform measure that I'm considering? Well, since this is a Hamiltonianly inclined audience, at least for the most part, with respect to the Liouville measure on the unit tangent bundle. Or if you're more algebraically inclined, it's simply the unique SL2R invariant measure on the homogeneous space gamma mod SL or PSL2R. So again, you have uniform equidistribution. As I mentioned, the result is non-effective. It relies on some ingenious thickening trick that allows to use the mixing properties of the geodesic flow on such quotients. Now, at the time where Margulis proved this result, effective versions of effective mixing for the geodesic flow was not yet known. It was only shown later by Marina Ratna in 1987. But anyway, if you try to make the argument effective, the thickening trick, which became known as the Margulis banana trick ever since, you can do this, but you have some loss you expect some loss of control on the exponent when you thicken the circle to perform this argument. That's why. But anyway, now the a precise asymptotic result for this statement is available. And in order to state it, let me just introduce the Laplace-Beltrami operator. So consider an effective, actually it's a precise asymptotic expansion for the rate of equidistribution, for the equidistribution rate is now available now. So let delta be the Laplace-Beltrami operator on my surface, my underlying surface gamma mod H. As it is well known, since the space is compact, it is so the spectrum of the Laplace-Beltrami operator is discrete, pure point, consists only of eigenvalues. The only accumulation point is at infinity. You can arrange this to be a sequence tending to infinity, pure point and contained in the positive half line. For any nu, that's the last bit of notation I shall introduce, for any nu in the spectrum, let nu be defined by the square root of 1 minus 4 mu, where I take this in with positive real or imaginary part, depending on the value of mu. And then the result is as follows. This is due to myself and Davide Ravotti this year. A precise asymptotic expansion for the rate of equidistribution. So let me choose, don't want to get bogged down in regularity questions. So let me directly choose some C infinity function, but it holds under much weaker regularity assumptions on the test function. So if I take a C infinity function on the unit tangent bundle, and actually the result is not only for circles, but also for any subarc. So I fix, in order to describe a subarc, I fix a parameter describing the length in, so not really the length, the renormalized length, but let me fix some parameter in 0 to pi. Then the result is that there exist some coefficients that exist for any nu in the spectrum, continuous functions d plus minus mu theta of f from the surface, sorry, from the unit tangent bundle to C, continuous. So some coefficients such that for any starting point P and for any time t, if I look at the average of f along the geodesic expansion of my original arc, so this is described by 1 over theta integral from 0 to theta of f composed with phi t, composed with, let me parameterize the circle, the unit tangent space at my fixed point P by Rs. Well, what's the asymptotic expansion of this? Of course, the constant term, as we know already by the result of Margulis, is the average of f over the whole space. Let me call it vol by the volume measure. And then I have all terms corresponding to the decomposition of my function according to Laplace eigenfunctions, or rather on the unit tangent bundle according to the Casimir eigenfunction, but I don't want to get into the representation theory of SL2R. So this is, anyway, I have here a term which is e to the minus t halves, and then I have a sum of oscillatory terms. So it's the sum over all Laplace eigenvalues bigger than 1/4 of an oscillatory term of this form, sinus imaginary part of mu over 2. So when mu is bigger than 1/4, mu is purely imaginary. T times this coefficient d plus theta mu f at the point P plus corresponding term. Then I have the contributions coming from what are called the complementary series representations of SL2, so the eigenvalues for between 0 and 1/4. And here I have a first term, which is e to the minus 1 minus mu, sorry, 1 plus mu over 2 t plus the corresponding, times the corresponding coefficient, plus e to the minus 1 minus mu halves t d minus theta mu. Then I have a contribution coming from the fact that 1/4 lies or not in the spectrum. So let me call that indicator function of 1/4 belonging to the spectrum times, so I have again a term e to the minus t halves d plus theta 1/4 plus t e to the minus t halves d minus theta 1/4. And finally, I have a remainder term, r theta of f pt, where this, in absolute value, is bounded by some universal constant depending only on the surface or ultimately on the lattice gamma, times some Sobolev norm, which I don't want to specify, of f, so some Sobolev norm. And then I have a term t plus 1 e to the minus t. So that's a full asymptotic expansion, at least to some order, of the equidistribution rate. And this is, of course, the last result I'm going to mention because my time is already up. But before concluding, let me make just a few comments. So first of all, this result, we were recently made aware of the fact that actually a similar result, but only an effective version, not a full asymptotic, was proven already 4 years ago by Samuel Edwards in an unpublished manuscript. This asymptotic expansion actually matches precisely what Ratner got for the precise asymptotic expansion of the mixing rate of the geodesic flow. Same exponents, actually it's the same method. We were inspired by her method, which is of spectral nature. You simply take a function, you decompose it into, say, Laplace eigenfunctions. And for each of them, the condition of being a Laplace eigenfunction can be translated into an ordinary differential equation for these averages, which you can explicitly solve. And this gives you essentially everything. The same asymptotic expansion would hold for geodesic, for expanding horocycle segments. If you take some segment of horocycle and you expand it by geodesic, you will have this precise same form for the asymptotic expansion. Of course, only the coefficient would be different, but the rate would be exactly the same. And to conclude and honor our spiritual host Riemann, let me also say that at this point, the natural question would be, well, what happens to the finite volume non-compact case? Of course, here the spectral method is extremely facilitated by the fact that M is compact. In the finite volume non-compact case, the spectral considerations become much more involved, in fact, so much more involved that the precise attaining such a result for geodesic expansions of horocycles, of closed horocycles, is known to be equivalent to the Riemann hypothesis by an observation due to Donzaguier in 1979. And I guess with this, that's all I wanted to say, and thank you very much for your attention.